So in this first lesson, we're going to explore periodic data. And this is the introduction to this unit on periodic functions and trigonometry. So trigonometry partly is the study of functions that repeat themselves. So that's where the name periodic comes from. So our objectives for today are to identify cycles and periods of periodic functions, and then be able to find the amplitude of a periodic function. So the period and amplitude are two important ways to describe a periodic function. So we're going to work through a little activity together here, and everyone's familiar with a Ferris wheel, right? So fun to ride these on the fair if you're not afraid of heights. So here's a Ferris wheel, and let's assume that it takes about 36 seconds to complete one full revolution. And the height of the car, when you're at the very bottom, we're going to call that at location 0, or our starting point, is already 5 feet above the ground. And then the diameter of the Ferris wheel itself is 40 feet. So if we're at the very top of the Ferris wheel, we would be a total of 45 feet above the ground. Now, we're going to work through and answer some questions about the motion of the Ferris wheel and our location on the wheel as it turns. And all these questions are going to be focused on the height. How far above the ground will we be at different points on the wheel as we rotate? So the first question says at 0 seconds. So when the ride starts, we're right at the very bottom. Let's say you're the last person to load onto the Ferris wheel. So it starts off and doesn't stop at that point. So how high will we be above the ground? Well, we already talked about that, right? That's the 5 feet that it starts at the bottom of the Ferris wheel. Now, what height will we be at 9 seconds later? So remember, it takes 36 seconds for one complete revolution. So 9 seconds is what fraction of 36? Well, if you know your arithmetic, you would realize that that's 1/4 of a revolution. So we would make 1/4 rotation or revolution of the Ferris wheel, which would take us halfway up on the side of the Ferris wheel, right? So that would be 25 feet. Now, why 25? Well, we have the 5 feet, we're already above the ground, plus half of the diameter of the wheel, which is 20. So we add those together and get 25. How about at 18 seconds? Well, 18 seconds, we're going to be at the top of the Ferris wheel, right? That's 1/2 of a revolution. And we've already said the very top will be 45 feet. And then what about 27 seconds? Well, 27 seconds is 3/4 of a full revolution. So we're going to be halfway down on the right-hand side. And so that would also have us 25 feet, the same height that we were going up on the left-hand side. Now, what if I ask you how many revolutions would be made after 126 seconds? Well, we would ask ourselves, how many cycles is 126 seconds? Well, that would be 3.5, right? We just divide 126 by 36 and we get 3.5. So now the question is, how high will we be after 3.5 rotations? Well, we don't really have to concern ourselves with the 3, right? A full rotation, whether it's 1 or 2 or 3 or 100, brings us back to the start. But we are concerned about the 0.5, right? Half of a revolution. And half of a revolution will put us back at the top of the Ferris wheel. So we would be at 45 feet. Now, see if you can predict where we'll be after 3 minutes. So remember to convert it to seconds. So 3 minutes is 180 seconds. And if we divide that by 36, we find that we have 5 full revolutions, which means we're going to be back where we started, only 5 feet from the bottom. Now, do you think you could sketch a graph of the relationship between your height above the ground and the time since the ride started? And we're going to do this for a domain, a set of x values, which represents time here, of 144 seconds. Okay, and we're going to start at the bottom of the Ferris wheel, so a height of 5 when time is equal to 0. Now, if you think about it, 144 seconds divided by 36, that's 4 complete revolutions. So we're going to get 4 cycles here on our graph. So let me go to a little larger view, right, for us to work on this. Here's the graph we want to fill in. Here is the Ferris wheel. Now, I've froze it here. We're not going to have it rotate, so we can identify some points on here. So at time equals 0, you can see the flashing red at the bottom here. We have a height of 5 meters or 5 feet. Now notice, why did I put additional red dots at 36, 72, 108, and 144? Well, remember the total time to go around 1 revolution is 36 seconds. So we're going to wind up back at that 5-foot height every 36 seconds. Okay. Now, how about where would we reach the top, the maximum height of 45 feet? Well, that's going to happen after 1/2 of a revolution, right? So half of 36 is 18, but we will also show up at that same height every 36 seconds, okay? Hopefully you're kind of getting the idea here of what we're doing. Now, what about halfway up, right? Or a quarter of a revolution? That would be 9 seconds, and we would be 25 feet above the ground, right? Half the diameter plus the 5 feet. So here we are at 9 seconds and 25, and then we're going to repeat that location every 36 seconds. And let's go one more position. What if we're halfway down on the right-hand side? Well, from the previous form we filled out, remember that was 27 seconds. So we're going to be also at 25 feet, but at 27 seconds, and then every 36 seconds after that. Now, if you look at how I've scaled this, right, each square is 6 seconds. So 36 seconds is going to be 6 squares. So we'll repeat these values for height every 6 squares. Okay, so we've got all these points on here. What would it look like if I tried to plot a line through them, a nice smooth line? This is what we wind up with. And notice this is different than any other function that we've worked with so far because it repeats itself, right? It has one unique set of values for the first 36 seconds, but then we go back over those same set of values every 36 seconds, and it would just continue on, right, infinitely, as long as the Ferris wheel continues to turn at that same rate. So this is what we call a periodic function. It repeats a pattern of y values at regular intervals. Notice it's the y value, or in this case, the height, right? Y axis stands for the height in our example. One complete cycle we call a period. And the period of a function is the horizontal length of one value. So how far along the x-axis do we have to move in order to trace out one full period? So let's label some things on here. And there's actually a couple different ways we could define a period. So we could define a period that starts at the yellow dot, right, which was halfway up, or 1/4 revolution, until we reach the next yellow dot. That would be one period, 36 seconds. We could also define a period as going from the maximum height to the next maximum height, our blue dots. That would have the same period. And we could even define one period as the lowest point, right, 5 feet, until we return to the bottom again. All of them have the same period. We've just been able to show or represent a period in 3 different ways on our periodic function. All right, so let's look at an example. If I ask you to identify the cycles and the periods of a graph, okay? So here's our function. And some of these are going to look kind of strange, right? But the key thing is, are they periodic? So can we identify the period or cycle in 2 different ways? So yeah, we can. We'll do that in a second. Here we go. So we could go from the peak, right, the most positive value, down to the most negative value, then back up to the peak again. That would be one cycle. And if we just count the squares, we got to be careful how we scale the x-axis here. We would see it has a period of 4. Or we could define a period from the lowest point and then back to that lowest point again. And that would have the same period of 4. There's even one more way, right? And this is somewhat arbitrary. You could pick any point on this graph, and as long as you return back to that same y value, that would be one complete cycle. All right, let's try another one here. See if you can figure out where you would draw a trace over the graph to represent one cycle. So here's one. We basically go from the x-axis 0 till it hits 0 again. And another one, we could go from the maximum value from +2 down to -2, back up to +2. What would the period be? Well, 4 units, no matter how we represent the cycle. All right, let's try another one. Is this function periodic? If it is, find the period. So it kind of looks periodic, but remember our definition. Our definition is that the same y value has to repeat. And you can see here, these yellow points I put on the graph kind of correspond to a certain cycle, but it's not the same y value each time. The y values are getting lower and lower. So since the y values are not repeating at the same number or value on the y-axis, we would have to say it's not periodic. All right, one more. Determine if it's periodic. If so, find the period. In this case, yes, right? We have 2 y values that are repeated here at the top of this periodic function. And therefore, we can define the period, right, between any 2 points that have the same y value. So we could go between the y value, or the yellow dots here, a period of 5. We could do the same thing between the red dots and have a period of approximately 5 squares. All right, last concept here. What do we mean by the amplitude of a periodic function? The amplitude has to do with the range between the minimum and the maximum values, and you determine it by taking half the difference between the maximum and minimum values of the function. So what do we mean by that? Let's look at an example here, right? I think we'd all agree, if we look at our kind of jagged periodic function here, the maximum value, y value that it reaches is 2. And the minimum value down below is -1. So the amplitude will be the difference of those 2 values and then divide by 2. So let's do that. 1/2 times, now multiply by 1/2 is the same as divide by 2, right? Hopefully you guys know that. The maximum is 2, and here we got to be careful with the signs. Notice our minimum is a -1. So the difference is actually 3 units, and we can see that on the graph, right? It's 3 squares between the maximum and the minimum. So 1/2 of 3 gives us 1.5. This function would have an amplitude of 1.5. So we can kind of draw a dashed line that's halfway between the minimum and maximum, and that would kind of represent the center line of our function. It's going to have values that are equally above and below that center line. So the amplitude really is the distance from that center line either to the maximum or to the minimum. So 2 ways to kind of draw or identify our amplitude. All right, let's look at a couple examples and then we'll wrap this up. Find the amplitude of the function. Well, what is our maximum? Our maximum is 1. Our minimum is -3. So the difference between that, and we could either do the math or just count the squares, right? But we see that the difference is 4. 1 minus a -3 will be 1 plus 3, or 4, and half of that is 2. right? So we can kind of draw our center line in here, and the amplitude would either be 2 above that or 2 below that. All right, let's try one more, see if you can determine the amplitude here. All right, here we go. Our maximum is 2. Our minimum is -3. We can count the squares, right? The difference is 5, so half of that would be 2.5. But let's go ahead and do the math. So 2 minus a -3 is +5. 5 divided by 1/2 gives us 2.5. So notice we'll always talk about the amplitude in terms of positive value. If I ask you to find the amplitude of the function, we're going to state it as a positive value. All right, now let's go back to our original example. What would the amplitude be of our function that we created from our Ferris wheel? Well, what is our maximum and minimum values, right? Our maximum is 45. Our minimum is 5. So the difference is 40, and half of that would give us 20 or 20 feet. So our function from the Ferris wheel gives us an amplitude of 20 feet and a period of 36 seconds. So how does that correspond to our Ferris wheel? Well, that amplitude is a distance, right, from the center of the wheel to the outer perimeter or circumference of the wheel. All right, so that's it. Pretty simple concept, but very important. We know how to identify cycles and periods of periodic function, and we know how to find the amplitude.